This is the hints video for Chapter 10 homework. In the first problem, we've got a hydraulic car lift in which compressed air exerts force on a piston of a given radius, and then the pressure is transmitted via hydraulic fluid to a larger radius piston. And the question is, what force must the air pressure exert in order to lift a car weighing 13,800 newtons? So what force must it push on at the smaller radius piston end? And in order to figure that out, we're going to use the fact that the pressure at the location, we're assuming that the heights of these two pistons are the same, so the fluid level, the hydraulic fluid level is the same. And therefore the pressure in the fluid is the same there. So P where the air is equal to P where the car is being lifted. And that means force divided by area at position 1 equals force divided by area at position 2. And in each case we can calculate the area as pi r squared, where I would convert the r, the radius, to meters, and that would give us an area in square meters. And the force required at the car end, of course, is 13,800 newtons. And so we know the A1, the A2, we know the F2. The only question is, what is F1? And we have F1 over A1 equals F2 over A2. Part 2, the question is, what air pressure will produce this force? Answer in units of Pascal. So we're just going to say the force that we just calculated in the first part is equal to pressure times area, or pressure is equal to force over area. So we're going to take the force we just determined and then divide by the area of the smaller piston and figure out what the required pressure is. Problem 3, suction cup on the ceiling. What must be the contact area between the suction cup completely exhausted? That means there's no air left underneath the suction cup. So it's stuck to the ceiling and there's no air between the rubber part and the ceiling. In order to support the weight of a 109 kilogram student. So the idea here is, well, suction cups are kind of confusing if you've never thought about them before. When you stick this thing on the ceiling, what is the force that's keeping it from falling away from the ceiling? And you might say, well, it's a suction force, but really, air pressure only pushes, it never pulls. Just because you have a vacuum in something, it isn't pulling, it's just that the air pressure everywhere else is pushing. So we better be able to explain this in terms of a pushing force. So if I have a circular cross-section cup and I'm hanging on it, I'm exerting a force down on the cup. What's the force that's pushing it up against the ceiling and counteracting that? It's the air pressure force from the outside. So in other words, the air pressure here near the surface of the Earth is pushing upward on that circular disc, which is the bottom of the suction cup, the part that's not stuck to the ceiling, and pushing it up, right? It's constantly hammering against it. And when it's just about to fall, in other words, we can hang more and more and more weight on it. When it's just about to fall, the air pressure on the outside, well, we can think of, there's really three forces on the suction cup, right? I'm pulling down on it, air pressure is pushing up on it from the bottom, and it's also possible that the ceiling is pushing down on it from the top. But if it's just about to fall, if we've hung the heaviest student on it that we possibly can, or if it's just about to fall, what that would mean is that the downward force from the ceiling goes to 0, and the upward force due to the air pressure on the bottom of the suction cup, the part that's not stuck to the ceiling, is equal to the downward force from the student. So we're just going to balance those forces. 109 kilograms times 9.8 must be balanced by atmospheric pressure, 101.3 times 10 to the 3 pascals, times the surface area of the suction cup, which in this case, well, we want to find that area, times A, and solve for A, right? We're going to do atmospheric pressure times the unknown A equals the weight of the student, 109 times 9.8. Next question. Similarly, we have a small piston, has a cross-sectional area of 3.6 square centimeters, and a large piston, larger surface area. What is the force that must be applied to the small piston? So how hard do we have to push down on this one to maintain the load of 77,000 newtons at the same height? So how hard, if we're holding something at the same height, how hard do we have to push down here to hold up something that weighs 77,000 newtons? And the idea is we're going to use the force divided by area here. The pressure at this surface is equal to the pressure at this surface. That means force divided by area here is equal to force divided by area over here. So we know this force, we want to know this. This is our unknown F times the given A over here is equal to the known F, which is 77,000 newtons, times the known A over here, and we can solve for the F that must be applied. Problem 5. A hollow brass tube has an outer diameter that's given. The tube is sealed at one end and loaded with lead shot, so it has a total mass of 7.5 grams, including the lead shot and the tube combined. The tube floats in water of density 1 gram per cubic centimeter. Sounds like, yes, we already knew the density of water, but it is told that it's water here. It's floating in a vertical position so that the circular end of the tube is down and it's floating straight up and down. What is the depth of the bottom end of the tube when it's sitting there floating in equilibrium? So we're just going to balance forces. We know that what are the forces that are being applied to the tube? Well, there's the weight of it pulling down from the earth, and there's also a buoyant force pushing up on it. And the idea is, well, the pressure force on the circular side of the tube isn't really helping to hold it up because it's pointing around the sides of the tube in a horizontal direction and towards the center of the tube, whereas the only thing that's helping counteract that vertical downward gravitational force is the pressure times the area upward on the bottom of the tube. And we know the pressure at the depth h is rho gh, where rho is, 1,000 kilograms per cubic meter. So rho gh, that's the pressure at depth h, times the area of the cross-sectional area of the tube. We use pi r squared there. In this case, they give the diameter, so make sure you divide the diameter by 2 to get the radius before you do pi r squared. Rho gh times pi r squared is equal to m times g, the mass of it, times the weight of it, mg. And you can solve for what h is. Bricks underwater. Imagine holding two identical bricks underwater. Brick A is just beneath the surface of the water, so it's completely submerged, but it's just right below the surface, and brick B is at a greater depth. What is the force needed to hold brick B in place compared to brick A? And the answer is here, it's the same as the force needed to hold brick A up. Even though the pressure is getting greater as you go down, both the pressure on the top, the downward pressure on the top of the brick, and the upward pressure on the bottom of the brick increase by the same amount. So the force downward on the top of the brick and upward on the bottom of the brick are getting bigger as you go down in the fluid, but the difference between those two pressures stays the same. And therefore, another way to think of it is, look, they have the same volume of water displaced, and therefore the weight of the water displaced is the same. So the buoyant force would be the same. And I've got to balance out my force plus the buoyant force is equal to the weight force. Well, the weight force isn't changing, the buoyant force isn't changing, and therefore my force isn't changing as we push it farther and farther down. Problem 7. Suppose a volleyball A floats on the surface and bowling ball B, which is denser than water, is submerged. Which feels the greater buoyant force? And again, we can use Archimedes' principle here. The buoyant force is equal to the weight of the water displaced. I think they have the same volume here, but only part of that volume is submerged in A. So B displaces water whose weight would fill the entire one, whereas A only displaces part of that amount of water. So the weight of the water displaced is greater in B, and therefore B feels a greater buoyant force, despite the fact that it sinks because it also has more mass, right? So that's just part of what's there. Problem 8, 20 Newton rock hangs from a spring scale. The rock is lowered into a beaker of water, and that beaker sits on another spring scale. It's not allowed to touch the bottom of the beaker, so it's just being held by this string in the middle of the fluid after they've done that. How does the reading on scale A change? So the idea is so essentially there's no buoyant force to speak of. There's a slight buoyant force due to the atmosphere being a fluid itself, but the pressure doesn't change as we go from the top of the rock to the bottom of the rock in terms of air pressure by any significant degree. But that's not true once it gets down in the fluid pressure increases rather quickly. So there's a significant buoyant force when it goes underneath. So when it's out of the fluid, the string has to hold up the entire weight, and so the scale will read the entire weight, whereas when it's underneath the fluid, the string plus the buoyant force has to balance out the entire weight, and therefore the string doesn't have to pull as hard. That means scale A's reading will go down, will decrease. Part 2, how does the reading on scale B change? Well, think of it with Newton's third law. When I submerge that rock underneath, the fluid is pushing upward on the submerged rock, and therefore the submerged rock is pushing downward on the fluid. That's Newton's third law. Whereas that wasn't happening before before it was submerged in. So therefore there's an additional downward force from the rock on the fluid, because the fluid's pushing up on the rock's pushing down on the fluid when it's submerged, and that's going to increase the reading of scale B. Problem 10. A cork is held at the bottom of a bucket of water by a piece of string. The actual depth of the cork is so many meters below the surface of the water. So here's a picture. This cork wants to float, but we've tethered it to the bottom with a piece of string. And here's the distance of the top of the cork. The depth of the cork is 0.7 meters, so maybe that's the distance to the center of the cork. If the density of the cork is such and such, and the volume of the cork, which is also given there, then what's the tension in the string? Well, if I want to know the tension in the string, it sounds like I should draw a free body diagram for the cork. What forces are being applied to it? Well, it has its weight force going down. It also has a tension force going down, and then it has a buoyant force going up. How are we going to fit? So let's the weight force we know how to do because, well, let's see. We need the mass of this. We're not given the mass, but we are given the volume of the cork and the density of the cork. So we know density times volume is equal to mass. So we multiply those two to get the mass of the cork. And then mg is a force going down, right? That's the weight force. We have the unknown tension force also going down. And then we have an upward force, which is the buoyant force, and that's the weight of the water displaced. And we could calculate that by, of course, we're going to convert this volume to SI units. It's in cubic centimeters, but change it to cubic meters. So convert cubic centimeters to cubic meters. That's the volume of the water displaced. If we multiply by the density of water, 1,000 kilograms per cubic meter, that would give us the mass of the water displaced. That's not what Archimedes' principle talks about. It doesn't talk about the mass of the water displaced, rather it talks about the weight of the water displaced. So we need to multiply that result times little g to get the weight of the water displaced. and that would be the upward buoyant force, right? So we have, if we call plus y up and we do sum of the force y components is equal to 0 because it's not accelerating, the buoyant force minus the tension minus mg is equal to 0, and solve for the tension there. This distance doesn't come into the problem. It's sort of a red herring for that problem. A block of given volume floats with a fraction 0.66 of its volume submerged. So that means 0.66 times 0.4 cubic meters is equal to the volume of the object that's actually sitting under the water. It's floating in a liquid which is slightly more dense than water, 1100 kilograms per cubic meter. Find the magnitude of the buoyant force. And so we use Archimedes' principle here. The buoyant force is the weight of the liquid displaced, or the fluid displaced, and we can get that by taking the volume of the fluid which is displaced, which is 0.66 times 0.4 cubic meters, times the density of the fluid, which is 1100 in SI units. That would be the mass of the water displaced, or the fluid displaced, and then multiply by little g to get the weight of the fluid displaced. That would be the magnitude of the buoyant force. Problem 12, a 1.4 kilogram beaker containing 1.7 kilograms of oil. So I think we add those two to get the total mass of the beaker plus oil. And we're told the density of the oil in the beaker as well. We take a 1.9 kilogram block of iron of given density, suspended from a spring scale and completely submerged in the oil as shown here, and the whole mess is sitting on top of another scale underneath, kind of like that problem we had above. Find the equilibrium reading of the spring scale on the upper scale. Okay, what does this spring scale read up here? To do that, we can do a free body diagram for the 1.9 kilogram mass. What forces does it have on it? Well, it has a tension T going up, and that's what we want to know. The tension T should be the reading on this spring scale. Tension T going up, a buoyant force going up, and a weight force going down. So we know the weight force, it's 1.9 times 9.8. The buoyant force is going to be the weight of the fluid displaced. This is oil, so it's not water here. So we're going to take the weight of the fluid displaced is going to be the volume of the chunk of iron. We're given the mass and we're given the density, and we know density times volume is equal to mass, so we can use that to solve for the volume of the chunk of iron, right? That is equal to the volume of the fluid displaced because it's completely submerged. Then we multiply that times the density of the fluid, volume of fluid displaced times the density of the fluid in my version of the problem. That is 927 kilograms per cubic meter. That would give us the mass of the fluid displaced, and then we have to multiply that mass times little g to get the weight of the fluid displaced. That's what Archimedes' principle says. So that would give us the buoyant force. And so we've got those three forces, tension going up, buoyant force going up, weight going down, and we can solve for the tension. Whatever the tension in the string is, that is supposed to be what the scale is calibrated to read. So we solve for the tension. That's the answer to the first part. And then the second part is, what is the reading on the lower scale? In this case, there are several ways we could do it. One way is to take your object for a free body diagram to be the beaker plus the oil plus the block that's sitting in it. Okay, what forces are being applied from the outside on that object? Well, we know the masses of all three of those, so gravity is pulling down on it. The scale is pushing up on it, and if we can find that scale force, that's what the scale is supposed to be calibrated to read. So, weight going down, bottom scale force going up, and then also the tension going up. We already solved for the tension, so we know the tension force going up, we know the weight force of all three things added together going down, and the unknown scale force going up. So set the sum of those forces, y components equal to 0, solve for that scale force up from the bottom, and that should be what it's calibrated to read. Problem 14. A block of metal suspended from a scale and immersed in water, as in the figure. The dimensions of the block are given. One of the dimensions is the vertical one, and the top of the block is so far below the surface of the water. So we're given this distance, the top of the block is below the surface of the water. We're also given the 3 dimensions, and we're told that one of them is the vertical dimension. What is the force exerted by the water on the top of the block? Well, that's the pressure at this depth times the area of the top of the block. So in my particular problem, that would be rho GH, where h is 5.4 centimeters or 0.054 meters. Calculate rho GH, and it's in water, so we're using rho is 1,000 in SI units. That's the pressure, and to get the force exerted by the water on the top of the block, we take the pressure at that depth times the surface area of the top of the block, and that's just the width times the length, or the 2 horizontal dimensions. So that would be 0.101 times 0.095 meters. So multiply those two together and multiply by the pressure at that depth from rho GH, and that would give us the force on the top of the block. Part 2, what is the force from the water on the bottom of the block? That's an upward force, and we just do rho GH, same kind of thing, but we need to use h corresponding to the bottom. So we add together the 5.4 centimeters plus 12.5 centimeters. Put that in meters and use rho GH times that same surface area of the bottom of the block. Part 3, what's the reading on the spring scale? Well, in this case, the reading on the spring scale can be gotten by balancing forces. This thing's in equilibrium, and therefore the sum of the forces in the vertical direction is equal to 0. We've got a tension force going up. That's what we want to solve for. We've got a buoyant force going up. That's equal to the weight of the water displaced, so we can get that by calculating the volume of this object, right? Converting those dimensions to meters in cubic meters, times the density of the fluid, and this is water, so times 1,000 will give us the mass of the water displaced, times little g will give us the weight of the water displaced. That's another force going up. So T going up, buoyant force going up, and weight going down. And in this case, we're told the mass of the block. So we just multiply m times g. Set those force y components equal to 0 and solve for T, and that's what the upper scale should read. 4. What is the buoyant force in this case? Well, we got that on the way to part 3, so we're already done there. Problem 18. A constriction in a pipe reduces its diameter from 6.5 centimeters to 2.7 centimeters. I guess I should make the warning here that, this is one case. I think there were several cases above where you might have been given a diameter, but just be careful. If you're going to use pi r squared, you got to divide the diameter by 2 to get the radius to use in pi r squared. So at the wider point, we're given the fluid velocity. Find the fluid velocity where it's more narrow. So we're going to use our continuity equation. A1v1 equals A2v2. And the a's are going to be the corresponding pi r squared. So divide those diameters by 2 and use pi r squared. So we've got our A1 V1, and we can calculate our A2, so we just need to solve for what V2 is. A cowboy at a ranch fills a water trough that is 1.2 meters long, 74 centimeters wide, 44 centimeters deep, so we should change those last 2 dimensions to meters, calculate the volume of the trough in cubic meters. Water emerges from the hose, which has a given diameter there at 1.1 meter per second. How long does it take to fill the trough? So the idea is here, if we could calculate what the volume flow rate, the rate at which volume is flowing, then the rate at which it's flowing times the time it takes is equal to the volume that's been filled up, right? Rate times time is always equal to the amount that's been discharged. So in this case, if we want to get the volume flow rate, we're given a velocity here, but we need the volume flow rate in cubic meters per second. And so to get the volume flow rate, we could think, well, in 1 second, how much volume of water comes out? Well, let's see. The diameter of the hose is 2.4 centimeters. Convert that to meters, 0.024 meters. Divide by 2, and take pi times that radius squared. That would give us the cross-sectional area of the pipe. In 1 second, we have that cross-section times 1.1 meter length of water. That cylindrical volume of water comes out. So we know what volume of water comes out in 1 second. So that's the volume flow rate of the water, that amount of water divided by 1 second. If we know the volume flow rate of water times the unknown time is equal to the volume that it's going to fill up in that time. So we set the volume that it's going to fill up to be whatever the volume of the trough is and solve for the time needed in that case. And that's all she wrote.